Hey everyone, Mr. Binder here. The topic that we're going to be covering today is water. Again, water is very important for cellular function. As you can see here in cellular respiration and photosynthesis, more specifically speaking, water is a product as a result of cellular respiration. Water is also a reactant as a result of photosynthesis. If you took a look at biological reactions, water is a product as a result of a dehydration synthesis reaction, or better known as a condensation reaction. And water is used in a hydrolysis reaction. A cell will use water to break apart larger macromolecules. There's a lot of properties that water does have because of its molecular structure here, and we will discuss some of those. Now, taking a look at the structure here, oxygen is covalently bonded to two hydrogen atoms. Now, covalent bonds share electrons, but the electrons want to spend more time on the oxygen atom. The reason for this is because oxygen has a higher electronegativity value than hydrogen, meaning that electrons want to spend more time around oxygen. And because electrons spend more time around oxygen, oxygen will have a partially negative charge. And because the electrons aren't going to spend as much time around the hydrogen atoms here, they are both going to have a partial positive charge. Now, a difference in charge across the molecule, the property to describe this is known as polarity. And this polarity is very, very important when describing some of the other properties of water. So what makes water so important? Well, it remains liquid over a wide range of temperatures, from about 0 to 100 degrees. It is polar, the uneven charge, which is very important in terms of its property to dissolve other substances. Again, water is known as the universal solvent, and the reason why is because of its polarity. You'll hear some terms like dissolves like, or polar dissolves polar. Well, if another molecule shares similar properties to water, chances are it will dissolve in water. Again, you take a look here, because of the partial charge of water, this partial negative charge and partial positive charge on the hydrogen atoms, there will be a van der Waals force, or a interaction between molecules, and this is known as a hydrogen bond. Hydrogen bonding occurs between polar molecules. The partially negative charge on the oxygen atom is attracted to the partially positive charge on the hydrogen atom, forming this type of intermolecular force, which is known as a hydrogen bond. And these are very important. Again, these hydrogen bonding between water molecules for its specific properties. Again, water, gradual change in temperature. It takes a lot of energy to heat up water 1 degree per kilogram. And again, another cool property of water is it expands when it becomes solid, forming a nice crystal lattice. And because it expands when it is solid, it is less dense than its liquid form, allowing it to float on water. Now, taking a look here, this is just to explain more of the polarity between a water molecule. Water is dipole in nature, meaning that there's a difference of charge across the molecule. Again, oxygen has a partially negative charge, while hydrogen atoms here have the partial positive charge. Taking a look at some of the properties of water here, when water freezes, it expands, becoming a solid. And because it expands, it is less denser than water. Well, this property allows ice to float on water, creating ecosystems for different organisms. It also insulates the water that's underneath it, preserving those aquatic ecosystems during harsh weather. High surface tension. This is created because of the cohesive nature of the water molecule. Because it's polar, hydrogen bonding is going to occur between each water molecule. Well, this hydrogen bonding allows these water molecules to want to stick together, creating this cohesion between water molecules. Well, this cohesion has everything to do with the surface tension. Low viscosity. Viscosity determines the thickness of a specific medium. Again, water can flow through very small spaces. It is a 3-atom molecule, very, very tiny. Liquid at room temperature. Again, cohesive properties, water sticking to each other. Adhesion is the other property that water can have. You might see this on glass. Water will stick to glass. And again, water acts as a universal solvent. Some terms here that we are going to talk about when describing how different substances or molecules react when they do come into contact with water is hydrophilic and hydrophobic. When there's a molecule that's hydrophilic, it is water-loving. It can dissolve in water. The examples of molecules that are hydrophilic are polar molecules, which are very similar to water. Like dissolves like, or polar dissolves polar. So molecules that are polar in nature love water and will also dissolve in water. Hydrophobic are molecules that are nonpolar, so they do not have a shared charge or a difference in charge across the molecule, so they will not dissolve in water. And again, this example here is the phospholipid bilayer that forms as a result of the properties of the molecule itself. It is both hydrophobic and hydrophilic, allowing this molecule to line up the way that it is, creating the phospholipid bilayer of our cellular membranes. Again, dissociation of water, this reaction does occur in our bodies. Water will break apart into the hydroxide ion and hydrogen ion, while some of the hydrogen ion will react with another water molecule, producing hydronium ion. And it's the concentration of this hydronium ion in solution that determines pH. Again, when the concentration of hydronium ion is equal to the concentration of hydroxide ions, that substance is considered to be in equilibrium. And if this substance is considered equilibrium or equal concentrations of each of these ions, well, the pH is 7. And this substance we're talking about here is pure water. Pure water is a neutral, has a neutral pH or pH of 7. Increases or decreases in pH will determine its acidity or basic alkalinity. Again, taking a look here, we see that pH is dependent on hydrogen ion concentration. So when an increase in hydrogen concentration occurs, pH will decrease. Again, we see as there's a decrease in hydrogen ion concentration, we see an increase in pH. So again, pH is dependent on hydrogen ion concentration. And this is what is going to determine acidic and basic environments. So we take a look here, pH. pH is, let's say, cytoplasm and lysosomes here, the difference in pHs of different substances. So that means that the concentration of hydronium ions or hydrogen ions is greater than the concentration of hydroxide ions. And this can happen when different substances dissolve in pure water. When substances dissolve in pure water, it can shift the amount of concentration of hydrogen ions in solution to either more or less. And dependent on if there's an increase in hydrogen ion concentration, you would see a decrease in pH, or if there was an increase in hydrogen ion concentration, you would see an increase in pH. So the question is here, you take a look, we have cytoplasm and we have lysosomes. Lysosomes an organelle in the cell. Cytoplasm is the fluid-like substance that is found in the cell as well. The question is, what is the hydrogen ion concentration for each of these? Well, cytoplasm here looks like 1 times 10 to the negative 7, and for lysosomes it looks like it's 1 times 10 to the negative 5. So how many times higher is the hydrogen concentration of lysosomes than cytoplasm? Well, whenever something moves in pH up a value, so let's go pH of 5, and then pH of 6, pH of 5 is 10 times more concentrated of hydrogen ions than pH of 6. So when we take a look at pH of about 7, 10 times 10 is about 100 times. So a pH of 5 is about 100 times stronger in pH than pH of 7. So taking a look here, lysosomes has a pH of roughly 5, which is 100 times stronger in pH than that of cytoplasm. A bicarbonate buffer system. This is something that our bodies use to maintain proper blood pH. And our pH, or proper blood pH, needs to remain about 7.35 to 7.45. And again, pH is concentration of hydrogen ions in solution. Again, hydrogen ion and hydronium ion, we can take a look at each of those. But for right now, let's take a look at concentration of hydrogen ion in solution. Well, our body is always trying to maintain proper pH of 7.3 to 7.4. And the system, the buffer system that our bodies use is the bicarbonate buffer system. This is the reaction here. Carbon dioxide reacts with water to form carbonic acid. Carbonic acid, a weak acid, will dissociate into bicarbonate ion and hydrogen ion. If there's higher concentration of carbon dioxide or higher concentration of bicarbonate ion or hydrogen ion, it can shift in one way or the next. If it shifts towards one side of the reaction here, what could happen are two different terms here that we're going to talk about: acidosis and alkalosis. Let's take a look at acidosis. Acidosis is when someone is experiencing a decrease in pH. So pH falls below 7.35. And what causes this? Well, increased CO2 blood levels, decreased bicarbonate ion blood levels, or there's limited hydrogen ion secretion from the kidneys. And when this occurs, when you have an increase in carbon dioxide, it's going to react with water to form carbonic acid. And when carbonic acid dissociates into bicarbonate and hydrogen ion, we see that there's an increased concentration of hydrogen ions, which will cause the decrease in pH, causing this acidosis. Now, what does our body do to help shift the equation back to equilibrium here? Well, or this buffer system back to equilibrium? Well, normal pH levels, our kidneys will secrete hydrogen ion because there's excess hydrogen ion, reabsorb bicarbonate ion, or what you could do is take bicarbonate supplements. Baking soda has some bicarbonate ion in it. You can take that to help restore balance of blood pH. Again, we take a look at some of the causes for acidosis. We see respiratory acidosis and metabolic acidosis. You don't need to know these terms, but just to take a look that if you have a respiratory disease, it could affect your blood pH. And again, taking a look at metabolic acidosis here, your kidney function, if it's not working properly, can affect your overall blood pH. Alkalosis, this is what happens when your pH rises above 7.4. Again, the reaction will tend to shift to the left. So causes here, carbon dioxide blood levels decrease, your bicarbonate ion blood levels will increase, hydrogen ions will react with the bicarbonate ion to form carbonic acid. So the reaction shifts towards the left here. Again, carbonic acid will dissociate into carbon dioxide and water in this case. Well, the decrease in hydrogen ion here is what will increase pH levels, and someone will experience this alkalosis. Well, to bring back normal blood pH, what our body will do is sometimes we'll take oxygen. Again, kidneys will secrete bicarbonate ion and reabsorb hydrogen ion. You could also take electrolyte supplements to shift the reaction back to the right and create this equilibrium. But again, some causes of alkalosis could be hyperventilating. Again, losing a lot of that carbon dioxide as a result of hyperventilating. High altitudes as well. Again, we take a look here with metabolic alkalosis. We don't need to know the difference between respiratory or metabolic alkalosis. Again, maybe some overuse of bicarbonate. Again, some medications can cause a shift in pH, or maybe loss of gastric juices. So again, take a look at these slides. More specifically, taking a look at the properties of water, you need to remind yourselves of some of the properties of water and how they are related to biology. And again, take a look at the slides as you go, and please review a lot of these topics.